Okay, here's a continuation, and we're going to do the two example problems. All right, here's a whole problem, so we're not just finding resistance. Okay, so one thing I could have asked for that I didn't was V1 and V2, which is short for voltage drop across resistor 1 and voltage drop across resistor 2. One reason I didn't ask it is because PVC. In parallel, voltage is constant. So if you look at this, and the voltage drops 9 volts, or raises 9 volts on the battery, that means it has to drop all 9 volts down this, or all 9 volts down that. Voltage is constant, so voltage is 9 here, it's 9 here, and it's 9 here. So that would have been too easy of a question. So that's why I didn't ask it. But I do want you to think of voltage drops as like a stairwell. The reason all of these have to drop 9 volts is your electricity can either go down this path or this path, and it has to lose all 9 volts. Think of you being like 9 volts in the air, and you got to drop all those 9 volts before you get back home. You got to spend them. Okay, so you can't just spend part of the 9 volts here. Even though they're different resistances, it still goes down the same height. And if you think of voltage as potential energy, it kind of makes sense considering it like height. And current is like kinetic energy. So their two currents are going to be different, but their voltages are the same. So how fast you go down, think of these like stairwells. This stairwell has less congestion on it, or it's a wider stairwell, so it has less resistance. This one's a skinnier stairwell. And if you were like leaving a sporting event, more people would be flowing down this wider stairwell, so more currents down here. This is a skinnier stairwell, so less people will be going down here, so a slower current. But do they both get down to the ground? Heck yeah, they do, so they have the same voltage drop. So that's just a fun little thing to remember. Anyway, let's do the problem. Enough talk. All right, if I want to find, if you do your work all in one spot and label your work well, like I do. Okay, if I'm looking for IT, current total, I need, well, think of Ohm's law, right? I put this off to the side. Ohm's law is VIR. So if I cover up the I, I'm looking at V over R. Now, if I'm looking for current total, I need voltage total over resistance total. Okay, I have my total voltage. It's the battery, 9 volts. Do I know my total resistance? Not yet. So before I do this question, I actually have to do this question. Resistance total, let me cover that up. Wait, we don't want that. Resistance total is what we were just doing up above. Let me do 1 over RT. Remember all this stuff? It's basically one of these problems. 1 over RT equals 1 over 200 ohms plus 1 over 100 ohms. Remember, if this were a series circuit, I would have just added 100 and 200 and called it 300. But it's not. This is a parallel, so I have to do 1 over that, and 1 over that, and 1 over my answer. Okay, so RT is going to be your answer. I already kind of know it because of proportions. If you're good at proportions, you can actually figure these out ahead of time. So flip it, and you get 66.6, because this is like 1/3 as big as that. So 2/3 of the current will be there. Anyway, don't worry about it. 66.6 repeating ohms. That's my total resistance. So 66.6 repeating ohms. That's an acceptable way to write your answer. Now that I have that, I can solve this guy up here. See how I'm separating my work? I can find my total current by taking my total voltage, 9, over my total resistance, 66.6 repeating ohms, and I will get my total current. So let's take 9 volts divided by 66 point, and just, if you put a ton of sixes, it actually does a great job. You get 0.135. What are my units on this for current? Amps. I used whole volts, I use whole ohms, I get whole amps. Problem is, I can't leave that as my answer. That's not proper engineering notation. So I'm going to move the decimal place over 3, and I get 135, and I got to remember That's little, so it's microamps. Or sorry, not micro, it's milliamps. So it's a M. If I would have moved it 6 places over and it's a tiny, tiny number, I would have done micro. But so I do want to keep this answer for later, though. I want to keep the regular one. I don't want to use this in the formulas because you got to use regular ohms and amps. All right, now if I want to find the amount of current, remember how I said people are going down these stairways differently? I would expect more resistance, so think of skinnier stairway. I would expect a slower current or less current going down here, and I would expect more current going down the wider hall, the wider stairwell. So when I go for I1 equals, remember cover this up, I is V over R. I is V1 over R1. So voltage drop across resistor 1 over resistance at resistor 1 will equal your current at resistor 1. So what's my voltage drop here? 9 volts, because PVC, right? So 9 volts over my resistance at resistor 1 is 200 ohms. And we're going to go 9 divided by 200 is 0.045 amps. And that's cool and all, but I got to move it over 3. So it's 45 milliamps for my answer. And then I2 is going to be V2 over R2. My voltage at 2 over my resistance at 2. Well, my voltage at 2 is still 9 volts. My resistance at 2 is 100 ohms. And 9 volts divided by 100 ohms. Oops. I don't even need a calculator for that, but I apparently did. So 0.09 amps. Move it over 3, not 2. And if you move it over an extra spot, you got to add a 0. So 90 milliamps. So is more current flowing down the wider stairwell? Yup, twice as much, which makes sense because it has half as much resistance. Awesome. Let's do another one. Okay. Woo, got a little crazier. Okay, we got a 30 volt power source here, and we got a triple resistor parallel. So when my current leaves here, usually the bigger end is your positive and the smaller end is my negative, even though I know it's wrong, but we're going to pretend current leaves the positive end, and now it has 3 choices. It can go down this stairwell, or this stairwell. Can't go down more than one, though. It's got to choose a path, and then it reconvenes and gets back here, right? So let's figure out our total resistance. By the way, what's our voltage drop at 1, and our voltage drop at 2, our voltage drop at 3? AKA, why didn't I ask for these? Because they are all 30 volts in parallel voltage is constant, right? So 30 volts, 30 volts, 30 volts. Think of this as another stairwell. You're up high, you have a potential energy of 30 volts, and you got to get down the stairs. You can choose this stairwell, that stairwell, that stairwell. Okay, and the flow of people will be different depending on how wide the stairwells are. Imagine the more resistance, the skinnier the stairwell is. All right, so let's do our work down here where we show our work. Find your total resistance first. That's kind of your step every time. So 1 over total resistance, this is like what we did, in the beginning of notes here, on the other page. It's 1 over, now I don't want kiloohms, I want to turn them all into ohms. So I'm going to move this back 3. 1,200 ohms. And this is 1 over 900 ohms. I don't want to compare kiloohms to regular ohms. And 2 kiloohms is 2,000 ohms. Okay, so my RT is going to be, I'll do 1 over 1,200 plus 1 over 900 plus 1 over 2,000. And then I'll flip this guy, boom. You get 409.09 ohms. Okay, is that number okay to keep? Heck yeah, it is. It's a number between 1 and 999. So 409.09 ohms is a good answer. Now I can find my total current, because total current equals, okay, remember our Ohm's law here, right? V, made that tiny, VIR. Okay, if I want my total current, it's V over R. So total current is total voltage over total resistance, right? So in this case, total voltage is 30 volts. Total resistance we just found, 409.09 ohms. And if you do 30 divided by 409.09, you get 0.0733 amps. Now that's not okay to leave that as your answer. You got to move it over until it's a number between 1 and 999. So I get 73.3 milliamps. Okay. And then we can do current at 1 and current at 2 and current at 3. So I1 equals V1 over R1. Okay. My voltage 1 is the same as my voltage anywhere because it's just a straight parallel circuit. My resistor 1 is the 1.2 kiloohms. Now don't use kiloohms. You have to, in Ohm's law, you have to use regular ohms. So I got 30 divided by 1200. I get 0.025 amps, which is 25 milliamps up here. And then we'll do the same thing for I2 and I3. I'll pause it here, do the work, so I'm not wasting time. Okay, so here's the work on the other two. Same deal as the first one, so you should be able to follow. And if you look at it, I turned them to milliamps, and what you should notice, this is Kirchoff's current law. If I add these three currents up, this path, and this path, it should equal my total current. In a parallel circuit, the three individual pathways, so it basically takes your 73 milliamps and splits it among these three pathways, which makes sense. If you think of it like 73 people are going down the steps at a time, it's got to split up amongst this stairwell, this stairwell, this stairwell, and they all go down the same amount, right? So all the currents add up to the total current. That's Kirchoff's law, and that's what we said like way back here. The sum of the current through each path is equal to total current. Okay, it also worked back here. If I would have added the individual currents, they equal the total current. All right, that's it. Talk to you later, people.